AI assistants like ChatGPT have become daily productivity tools for many people. However, the underlying technical principles remain a mystery to most. For those who don't understand the mechanics, harnessing the full power of AI isn't so straightforward. For example, what should you do when an AI confidently spouts nonsense or fails to help with even simple math calculations? Hey there, I'm Lily, a course instructor with millions of views and dedicated to creating the easiest to understand programming tutorials in the galaxy. But this new popular science course on large language models isn't about writing code, nor does it require any computer science background. I simply want to share some simple, easy-to-digest insights to help you understand the principles behind today's trending large language models. This will give you a foundational understanding of generative AI, a technology that can significantly impact technological development, business, and society. On the 30th of November 2022, OpenAI released ChatGPT, and its popularity swept across the internet. While Facebook took 10 months to reach 1 million users, and Instagram took 2.5 months, ChatGPT achieved this milestone in just 5 days. This was quickly followed by a large-scale model arms race among major companies, especially in the field of AI chat assistants. Google launched Bard, Microsoft introduced Bing AI, and Anthropic released Claude. With so many emerging large model applications, it's easy to feel overwhelmed by the dazzling array of options. When technology evolves too rapidly, it can also bring a sense of powerlessness, as if we can't keep up with the pace of development. But beneath the ever-changing surface lies a constant core. I hope to use a series of short popular science videos to help you understand the technological foundations behind these applications, so you can adapt to change with timeless knowledge. After building a preliminary understanding of the underlying technology, you'll be able to gain deeper insights into AI model performance and learn how to apply and fine-tune AI models more effectively. For instance, you'll understand why large language models sometimes hallucinate or confidently state false information, why they struggle with mathematical operations, what steps can lead to more accurate answers, and how to fine-tune a personalized model, among other topics. To reiterate, this popular science course series doesn't require a programming background or prior knowledge of AI. It's beginner-friendly. If you're interested in updates to this series, remember to follow me so you don't miss out. If you'd like hands-on learning on how to use large models to build AI applications, you can also look forward to my upcoming application development course. But for now, this theoretical course will focus on helping you understand the underlying principles. See you in the next video. Welcome to the first lesson of the AI Large Model Popular Science course for everyone. What is AIGC? Let's clarify a bunch of AI-related tech terms. When it comes to recent hot tech buzzwords, AIGC undoubtedly ranks among them. But do you really understand AIGC? Starting one day, we suddenly discovered that AI can help generate text, images, audio, video, and more. So well that it's often hard to tell whether the creator behind the content is human or AI. This AI-generated content is called AIGC, short for CV-generated content. Examples like articles generated by ChatGPT, code generated by GitHub Copilot, and images generated by Midjourney all fall under AIGC. While AIGC has been trending, another term has also gained popularity: full generative AI. From a literal perspective, the relationship between generative AI and AIGC is easy to understand. The content generated by generative AI is AIGC. Therefore, ChatGPT, GitHub Copilot, Midjourney, and others all belong to generative AI. As you can see, the concepts of AIGC and generative AI are quite straightforward. However, since the term AIGC is more popular in China than generative AI, in many contexts, AIGC is also used to refer to generative AI. So, what is the relationship between generative AI and terms like AI, machine learning, supervised learning, unsupervised learning, reinforcement learning, deep learning, large language models, and more? Does it feel tangled and complicated? It's hard to sum it up in one sentence, but a single diagram can help you visually understand their relationships. AI, also known as artificial intelligence, is a discipline under computer science. It aims to enable computer systems to simulate human intelligence to solve problems and complete tasks. AI was established as an academic field as early as 1956 and has experienced multiple cycles of boom and bust over the decades. Machine learning is a subset of AI. Its core idea is to allow computers to learn and improve on their own through algorithms, without explicit programming by humans, to recognize patterns, make predictions, and decisions. For example, if we tell a computer through code that red in an image means rose and orange means sunflower, the program's judgment about flower types is achieved through direct and explicit human-written logic. This is not machine learning. The machine hasn't learned anything. But if we provide the computer with a large number of rose and sunflower images, allowing it to recognize patterns and summarize rules on its own, so it can predict and judge unseen images, that's machine learning. Machine learning has several branches, including supervised learning and reinforcement learning. In supervised learning, the machine learning algorithm receives labeled training data. Labels are the expected output values, so each training data point includes both input features and the expected output. The algorithm's goal is to learn the mapping between input and output, so that given new input features, it can accurately predict the corresponding output. Classic supervised learning tasks include classification, which divides data into different categories, and regression, which predicts numerical values. For example, training a model with a bunch of cat and dog photos along with their corresponding cat or dog labels, then having the model predict whether an unseen photo is a cat or a dog. This is classification. Training a model with housing data like area, number of bedrooms, balcony availability, etc., along with corresponding house prices as labels, then having the model predict the price of an unseen house based on its features. This is regression. Unlike supervised learning, unsupervised learning uses data without labels. The algorithm's task is to independently discover patterns or structures in the data. Classic unsupervised learning tasks include clustering, which groups data. For example, providing a collection of news articles and having the model automatically organize similar articles based on themes or content features. Reinforcement learning involves a model taking actions in an environment, receiving feedback on the results, and learning from the feedback to take the best actions in given situations to maximize rewards or minimize losses. It's like training a puppy. At first, the puppy will act randomly, but as it interacts with the trainer, the puppy discovers that certain actions earn treats, some earn nothing, and others might even result in punishment. By observing the connection between actions and rewarding punishments, the puppy's behavior gradually aligns with the trainer's expectations. Reinforcement learning can be applied to many tasks, such as teaching a model to play Go. The model receives feedback on rewards or losses resulting from different actions, optimizing its strategy over multiple games to learn how to take actions for a high score. Now, the question is, where does deep learning fit among these three? It doesn't belong to any of them. Deep learning is a method within machine learning. Its core lies in using artificial neural networks to mimic the way the human brain processes information, extracting and representing data features through a hierarchical approach. Neural networks consist of many basic computing and storage units called neurons. These neurons process data through layered connections, and deep learning models typically have many layers, hence the term deep. For example, to enable a computer to recognize a photo of a kitten, in deep learning, the data is first passed to an input layer, much like how human eyes see an image. Then, the data goes through multiple hidden layers, each performing complex mathematical operations to help the computer understand features in the image, such as the kitten's ears, eyes, etc. Finally, the computer outputs an answer indicating whether it's a photo of a kitten. Neural networks can be used in supervised learning, unsupervised learning, and reinforcement learning, so deep learning is not a subset of them. Generative AI is an application of deep learning. It uses neural networks to recognize patterns and structures in existing content, learning to generate new content in forms such as text, images, audio, and more. Large language models, also known as LLMs, are another application of deep learning, specifically designed for natural language processing tasks. The large in large language models indicates that the model has a massive number of parameters, potentially tens of billions to trillions, and requires vast text datasets during training. This enables them to better understand natural language and generate high-quality text. There are many examples of large language models, such as GPT and Llama internationally, and Ernie and ChatGPT domestically, which can perform text understanding and generation. Taking the GPT-3 model as an example, it generates text sequences step by step by calculating probabilities based on input prompts and previously generated words or tokens. However, not all generative AI models are large language models, and whether all large language models fall under generative AI is somewhat debatable. The first part is easy to understand. Diffusion models that generate images are not large language models, as they don't output text. At the same time, some argue that not all large language models are generative AI because certain models, due to their architectural characteristics, are not well suited for text generation. Google's BERT model is an example. It has a large number of parameters and training data, qualifying it as a large language model. In terms of application, BERT excels at understanding context, so Google uses it in search to improve ranking accuracy and information extraction. It's also used for tasks like sentiment analysis and text classification. However, BERT is not adept at text generation, especially coherent long-form text generation. Therefore, some argue that such models do not fall under the category of generative AI. These concepts collectively form the core elements of generative AI, and I hope this helps you gain a better understanding of the trending AI GC. In the next section, we'll delve deeper into large language models. See you in the next video. On the 30th of November 2022, OpenAI released ChatGPT, which quickly became the fastest online product to reach 1 million users and also propelled large language models ILMs into the spotlight. More AI chat assistants have since sprung up like mushrooms, appearing in everyone's view. But do you really understand large language models? A large language model, or LLM, is a deep learning model designed for natural language-related tasks. Given some textual input, it can return corresponding output. Specific tasks it can accomplish include generation, classification, summarization, rewriting, and more. First, a large language model needs to undergo unsupervised learning on vast amounts of text. Taking GPT-3 as an example, its training data consists of multiple internet text corpora, covering online books, news articles, scientific papers, Wikipedia, social media posts, and so on. With the help of massive training text data, the model can better understand the relationships between words and their context, thereby improving its comprehension of text meaning and generating more accurate predictions. However, the large language models refers not only to the enormous training data, but also to the huge number of parameters. Parameters are internal variables of the model. Think of them as the knowledge the model acquires during training. They determine how the model responds to input data, and consequently, its behavior. Past research in language modeling has found that training models with more parameters, using more data and computing power, often leads to better performance. It is like teaching an AI to bake a cake. If you only allow the AI to adjust the amounts of flour, sugar, and eggs, versus allowing it to adjust flour, sugar, eggs, cream, milk, baking soda, cocoa powder, as well as oven time and temperature, the latter with more adjustable variables, enables the AI to better mimic and create a tastier cake. As the number of parameters increases, it might even gain the ability to create other things, inventing entirely new varieties. So today, the number of parameters in language models can be tens of thousands or even millions of times greater than before. Take OpenAI's first large model, GPT-1, as an example. It had 117 million parameters. GPT-2 had 1.5 billion parameters, and GPT-3 grew to 175 billion parameters. This allows large models, unlike smaller ones, to not be limited to single or few specific tasks, but to possess much broader capabilities. For instance, previously we might have needed to train separate models for tasks like summarization, classification, extraction, etc. But now, one large model can handle all of these. AI chat assistants like ChatGPT, Claude, and others are all applications based on large language models. If the stunning debut of ChatGPT at the end of 2022 was a milestone that significantly raised public awareness of large language models, the technological development milestone actually dates back to 2017. In June 2017, the Google team published a paper, "Attention is All You Need," proposing the transformer architecture. Since then, the direction of natural language processing has been transformed, leading to a series of models based on the transformer architecture. In 2018, OpenAI released the GPT 1.0 and Google released BERT. In 2019, OpenAI released GPT 2.0, Baidu released Ernie 1.0, and so on. So the development of large language models has long been in full swing. It is not that breakthroughs only happened in 2022, as many might think. But because ChatGPT was directly open to the public and allowed users to interact via conversation on a web page with a smooth and seamless experience, it captured the attention of the masses. The model behind ChatGPT, GPT, stands for Generative Pre-trained Transformer, indicating that transformer is key to its architecture. Therefore, to understand large language models, one cannot skip the transformer. Before the transformer architecture was proposed, the mainstream architecture for language models was mainly recurrent neural networks, RNNs. RNNs process text sequentially, word by word. The output at each step depends on the previous hidden state and the current input. Moreover, the current computation cannot proceed until the previous step is completed, making parallel computation impossible and training efficiency low. Additionally, RNNs are not good at handling long sequences, i.e., long texts. Due to the architectural characteristics of RNNs, the influence of earlier words on later ones weakens as the distance between them increases, making it difficult for RNNs to effectively capture long-range semantic dependencies. But in human natural language, it is very common for dependent information to be far apart. For example, in this sentence, the key to correctly predicting the next word is New York, which is quite far away. If an RNN were to generate the following content, by this point, it might have already forgotten the earlier information. To capture long-range dependencies, improved versions of RNNs later emerged, such as LSTM, Long Short-Term Memory Network. However, this still didn't solve the problem of traditional RNNs being unable to compute in parallel, and they still faced limitations when processing very long sequences. Then came the transformer, which has the ability to learn the relevance and context of all words in the input sequence, unaffected by short-term memory limitations. The key to achieving this lies in the transformer's self-attention mechanism. As the paper's title says, attention is all you need. Simply put, when the transformer processes each word, it not only pays attention to the word itself and its nearby words, but also to all other words in the input sequence, assigning different attention weights to each. These weights are gradually learned by the model during training through vast amounts of text. Thus, the transformer can understand how strongly the current word is related to other words and focus on the truly important parts of the import. Even if two words are far apart, the transformer can still capture the dependency between them. For example, in this case, grammatically speaking, it could refer to the closer street or the farther animal. Here, the self-attention mechanism captures a stronger relationship between it and animal, thus focusing more on animal. Besides the self-attention mechanism, another key innovation of the transformer is positional encoding. In language, order matters. Even if a sentence contains the same words, different orders can lead to vastly different meanings. That is why in the field of natural language processing, the term sequence is used. It denotes a series of elements arranged in a specific order. As mentioned earlier, RNNs, like humans reading text, process the input sequence sequentially, which creates a bottleneck in training speed because it can only be done serially, not in parallel, meaning it can't learn all information simultaneously. The transformer, before feeding words into the neural network, not only embeds the words converting them into vectors, i.e., representing each word as a series of numbers, but also represents each word's position in the sentence as a series of numbers, adding this to the input sequence's representation before giving it to the neural network. Thus, The model can understand both the meaning of each word and capture their positions in the sentence, thereby grasping the sequential relationships between different words. With positional encoding, words can be input to the transformer out of order. The model can process all positions in the input sequence simultaneously without needing to handle them one by one, like RNNs. During computation, each output can be calculated independently without waiting for results from other positions, greatly increasing training speed. With faster training, creating huge models isn't as difficult anymore, since the publication of attention is all you need. The transformer and its variants have been widely used to train large language models on massive datasets. Therefore, the transformer architecture is indispensable for the many powerful large language models we have today. If you are curious about how the transformer works in detail and how the GPT model behind ChatGPT generates text, the next section will provide a more detailed introduction. See you in the next video. Regarding the technical principles behind generative large language models, like GPT, a common explanation is that they generate text by predicting the next word with the highest probability. This effect is somewhat similar to the autocomplete feature in search engines. Whenever we type a new character or word, the input box starts predicting the following text, with higher probability suggestions ranked at the top. But how exactly does the model determine the probability of each word appearing? This video will reveal the principles behind ChatGPT for you. In our previous video introducing large language models, we mentioned that when discussing their technical principles, we have to talk about the transformer architecture. Since the 2017 paper Attention is All You Need introduced the transformer, it has virtually dominated the field of large models for text. Models like OpenAI's GPT, Xinhua's GLM, and Baidu's Ernie all have the transformer at their core. In the Attention is All You Need paper, it looks like this, a bit complex at first glance. But don't worry, it can be seen as consisting of two core parts, the encoder and the decoder. Suppose we want this transformer to perform an English to French translation task. We feed an English sentence into the encoder, and the decoder returns the corresponding French sentence. What happens during this process? Let's first look at the encoder part. The input text is first tokenized, meaning it is split into individual tokens. A token can be understood as a basic unit of text. Depending on the tokenization method, short words might each be one token, while long words might be split into multiple tokens. Then, each token is represented by an integer number, called a token ID. This is because computers cannot store text internally. Any character must ultimately be represented by numbers. With the input text represented numerically, it is then passed to the embedding layer. The role of the embedding layer is to represent each token as a vector. A vector can be simply thought of as a series of numbers. To fit it into the visual here, the vector length is simplified to 3. But in reality, vector length can be very long. A question arises. We already represented each token with a single integer earlier, so why now represent each token with a series of numbers? One reason is that a series of numbers can convey more meaning than a single number, containing more grammatical, semantic, and other information. It is like the words man and woman. They both describe humans, but their genders are completely opposite. If represented by only one number, should the difference between these numbers be large or small? But with multiple numbers, we can represent more dimensions. For example, the first number could represent the degree of being female, the second the degree of being older, and the third the degree of higher social class. So, the vectors from the embedding layer aren't arbitrary. They contain grammatical and semantic relationships between words. The embedding vectors of similar words are closer in vector space, while unrelated words are farther apart. This helps the model use mathematics to calculate distances in vector space and capture similarities between different words in terms of semantics, grammar, etc. Moreover, the difference between man and king and the difference between woman and queen can be seen as similar, which can also be represented in multidimensional vector space. Therefore, word vectors can not only help the model understand the meaning of words, but also capture complex relationships between them. For intuitive visualization here, we use a three-dimensional vector space, simplifying the vector length to 3. In the paper proposing the transformer, the vector length was 512, and in GPT-3 it is 12,288, so you can imagine how much information can be contained. After obtaining word vectors through the encoder's embedding layer, the next step is to add positional encoding to the vectors. In the previous video, we mentioned that a key mechanism of the transformer is positional encoding. If you missed the last section, no problem. Positional encoding involves adding a vector representing each word's position in the text to the word vector from the previous step, then passing the result to the encoder. The significance of this is that the model can understand both the meaning of each word and capture its position in the sentence, thereby grasping the sequential relationships between different words. Next, we come to the core part, the encoder. Its main task is to transform the input into a more abstract representation. This representation is also a vector, a series of numbers that retains both the lexical information and sequential relationships of the input text, while also capturing key grammatical and semantic features. The core mechanism for capturing key features is the encoder's self-attention mechanism. When processing each word, the model not only focuses on the word itself and its nearby words, but also pays attention to all other words in the input sequence. As the Transformer paper's title says, attention is all you need. The self-attention mechanism determines attention weights by calculating the relevance between each pair of words. If two words are more strongly related, the attention weight between them will be higher. For example, in this case, grammatically, it could refer to animal or street. The self-attention mechanism discovers a stronger association between it and animal, so it assigns a higher weight to animal. Due to the self-attention mechanism's comprehensive focus on context, the resulting output representation not only contains information about the word itself, but also incorporates relevant information from the context. Context is crucial in language and can reveal different meanings of the same word. So, in the encoder's output, the vectors representing each word are adjusted based on contextual information. The same word can have different abstract representations, depending on the context. The self-attention mechanism involves many computational steps. This video is mainly a simple introduction. More details can be found in the original paper. Moreover, the transformer actually uses multi-head self-attention, meaning the encoder doesn't have just one self-attention module, but multiple. Each head has its own attention weights, focusing on different features or aspects of the text, for example. Some might focus on verbs, others on modifiers, some on sentiment, others on named entities, etc. And they can perform parallel computation, meaning their progress doesn't interfere with each other. The weights for each self-attention head are learned and adjusted by the model during prior training from vast amounts of text. Following the multi-head self-attention, there is also a feed-forward neural network that further processes the output of the self-attention module, enhancing the model's expressive power. There isn't just one encoder in the transformer, multiple are stacked together. Each encoder has the same internal structure but does not share weights. This allows the model to understand the data more deeply and handle more complex textual content. After looking at the encoder, let's move to the decoder. It is key to how large language models generate words one by one. Through the previous encoder, we have an abstract representation of each token in the input sequence, which can be passed to the decoder. The decoder also first receives a special value indicating the beginning of the output sequence. The reason is that the decoder uses both the abstract representation of the input sequence from the encoder and the previously generated text as input to maintain coherence and contextual relevance in the output. In this initial round, there isn't any generated text yet, so the special start token is used as input first. The specific generation process still involves multiple steps. First, similar to the encoder, the text goes through the embedding layer and positional encoding we already know about, then is fed into a multi-head self-attention layer. But it is slightly different from the self-attention layer in the encoder. When the encoder processes each word, it can attend to all other words in the input sequence. However, in the decoder, self-attention only focuses on the current word and the words before it. Words after it are masked and not attended to. This ensures that when the decoder generates text, it follows the correct temporal order. It cannot peek at future words. when predicting the next word, it only uses preceding words as context. This type of multi-head self-attention is called masked multi-head self-attention. Masked multi-head self-attention operates on the already generated output sequence. After that, the decoder has another multi-head attention layer. This is where the abstract representation of the input sequence, output by the encoder, comes into play. The attention here captures the correspondence between the encoder's output and the output about to be generated by the decoder, thereby integrating information from the original input sequence into the generation process of the output sequence. The feed-forward neural network in the decoder functions similarly to the one in the encoder, enhancing the model's expressive power through additional computation. And like the encoder, the decoder also consists of multiple stacked layers. This can improve the model's performance and help handle complex input-output relationships. The final stage of the decoder includes a linear layer and a softmax layer. Together, their role is to transform the decoder's output representation into a probability distribution over the vocabulary. This probability distribution over the vocabulary represents the likelihood of the next generated token, with some tokens having higher probabilities than others. In most cases, the model selects the token with the highest probability as the next output. Now we know that the decoder essentially guesses the next most likely output. As for whether the output aligns with objective facts, the model has no way of knowing. That is why we often see the model confidently stating falsehoods, a phenomenon also known as hallucination. The entire decoder process repeats many times, with new tokens continuously generated until a special token indicating the end of the output sequence is produced. Then we have the complete output sequence from the decoder. Congratulations! The above describes the original transformer from attention is all you need. The encoder is used to understand and represent the input sequence, and the decoder is used to generate the output sequence. In practice, based on the original architecture, several variants have emerged, mainly falling into three categories: encoder-only decoder, only and encoder-decoder. Encoder-only models, also called auto-encoding models, retain only the encoder from the original architecture. BERT is an example of such a model. These models are suitable for language understanding tasks, such as masked language modeling, guessing masked words in text, sentiment analysis determining if text sentiment is positive or negative, etc. Decoder-only models, also called autoregressive models, retain only the decoder from the original architecture. The GPT series are examples of such models. These models excel at text generation by predicting the next word, as we've seen with ChatGPT. Encoder-decoder models, also called sequence-to-sequence models, retain both the encoder and decoder from the original architecture. Models like T5 and BART are examples. These models are suitable for tasks that transform one sequence into another, such as translation, etceterization, etc. After this video, your understanding of the technology behind large language models should surpass that of more than 99% of people. If you are curious about how to actually build a ChatGPT, see you in the next video. Putting an elephant into a refrigerator takes just 3 steps. To get a ChatGPT, how many steps does it take? Also 3 from step 1. Through a vast amount of text, perform unsupervised pre-training to obtain a base model capable of text generation. Step 2. Using some high-quality dialogue data written by humans, conduct supervised fine-tuning of the base model to obtain a fine-tuned model. At this stage, the model not only continues text but also gains better conversational abilities. Step 3. Use data consisting of questions and multiple corresponding answers, and have human annotators rank the answers by quality. Then, based on this data, train a reward model that can predict scores for answers. Next, have the model from step 2 generate answers to questions. Use the reward model to score those answers, and utilize the scores as feedback for reinforcement learning training. And just like that, ChatGPT is forged. Got it. If you want to understand the steps in more detail, keep watching. In the pre-training of step 1, a massive amount of text is first needed as raw material for the model to learn from. For example, the training data for the GPT-based model includes multiple internet text corpora covering books. news articles, scientific papers, Wikipedia, social media posts, etc. The overall scale of the training data is 300 billion tokens. If you're not familiar with what a token is, it generally refers to a basic unit of text for a large language model. For short English words, one word might be one token, while longer words might be split into multiple tokens. As for Chinese, the number of tokens tends to be relatively higher. Some characters may require one or even more tokens to represent. Back to our topic. With a large amount of text available for training, the model is trained using unsupervised learning. In contrast to unsupervised learning, supervised learning involves the model receiving labeled training data. Labels are the desired output values, so each training data point includes both input features and the expected output value. Unsupervised learning, on the other hand, lets the model train on unlabeled data, requiring it to find structures and patterns in the data on its own. Taking GPT as an example, during training, it uses vast amounts of text to autonomously learn the grammar, semantics, and expressive structures and patterns of human language. Specifically, the model first sees a portion of text and attempts to predict the next token based on the context. Then, by comparing the correct answer with its prediction, the model updates its weights, gradually learning to generate reasonable subsequent text based on preceding context. As it sees more and more text, its generation ability improves. If you're interested in the internal details of how the model generates text, you can watch my previous video. Pre-training is not an easy process and is the most time-consuming, labor-intensive, and costly step among these four. Taking GPT as an example, although official data hasn't been released, it is roughly estimated that it took months of training, using hundreds or thousands of EC00 GPUs, and costing several $1 million. The result of pre-gen training is a base model. The base model is not the same as the conversational model behind ChatGPT because, at this stage, the model can predict the next token and continue text based on context, but isn't skilled at conversation. If you give it a question, it might mimic the preceding text and help generate more questions instead of answering yours. To address this, we need Step 2, fine-tuning the base model. Fine-tuning involves further training on an existing model, altering its internal parameters to make it more suitable for specific tasks. In other words, to train an AI assistant good at conversation, the base model needs to be exposed to more dialogue data. However, the cost of fine-tuning is much lower compared to pre-training, because it requires a smaller scale of training data and shorter training time. At this stage, the model doesn't need to learn from vast amounts of text, but learns from some professionally written, high-quality human dialogues. This is equivalent to providing the model with both questions and the answers we humans prefer, falling under supervised learning. Hence, this process is called supervised fine-tuning (ST). After completion, an SFT model is obtained, which is better at answering questions than the base model from Step 1. But to further enhance the model's capabilities, Step 3 can be performed, having the SFT model undergo reinforcement learning. Reinforcement learning involves the model taking actions in an environment, receiving feedback on the results, and learning from that feedback to take the best actions in given situations to maximize rewards or minimize losses. It is like training a puppy. Through interactions with the trainer, the puppy discovers that certain actions earn treats, some yield none, and others might even result in punishment. By observing the link between actions and rewards, punishments, the puppy's behavior gradually aligns with the trainer's expectations. Getting ChatGPT's model to obediently serve as a helpful AI assistant follows the same principle. We can have ChatGPT answer questions and then have human evaluators score those answers. Scoring is mainly based on the 3H principles: helpful, honest, harmless. Helpfulness, assessing the model's ability to follow user instructions and infer intent. Honesty, evaluating the model's tendency to hallucinate, fabricate facts. Harmlessness, judging whether the model's output is appropriate, defamatory, or contains derogatory content. If the score is high, the model learns to keep up the good work. If low, it learns to improve. However, relying on humans to score each answer individually is extremely costly and inefficient, so why not train another model to score the model's outputs? Therefore, in this step, a reward model needs to be trained. It learns from question-answer pairs and their corresponding scores. The scoring data is obtained by having the fine-tuned GPT model. The SFT model from step 2 generate multiple different answers for each question, then having human annotators compare and rank the answers by quality. Although it still requires annotators' labor, once enough ranking data is gathered, it can be used to train the reward model, allowing it to learn to predict answer scores. Once the reward model is trained, it can be used in reinforcement learning. In reinforcement learning, ChatGPT's initial parameters come from the previously obtained SFT model, but are updated during training. The reward model's parameters are frozen. Its task is solely to score the model's generated content. After rounds of iterations, the model continuously optimizes its strategy, further improving answer quality. The powerful ChatGPT is thus forged through continuous learning. The rest of the story we all know. In November 2022, ChatGPT was released to the public, igniting the era of generative AI. If this video was helpful to you, please give it a thumbs up. In the next section, we'll explore how to properly train and interact with AI chat assistants, like ChatGPT. See you in the next video. Have you noticed that AI chat assistants like ChatGPT sometimes resemble a well-read and empathetic genius, while at other times they seem like a babbling fool who has had a bit too much to drink? In response to this phenomenon, more and more people are starting to research how to train a smarter AI chat assistant. Prompt engineering is the study of how to improve the quality and efficiency of communication with AI, with a core focus on the development and optimization of prompts. Prompts are the questions or instructions we input into the AI chat assistant, and the AI responds based on the content of the prompt. Before diving into prompt engineering, we first need to understand the limitations of chat assistants like ChatGPT. The large language models behind them are trained on massive amounts of text, so they excel at imitating human language and have absorbed a lot of knowledge from that content. Their responses are generated by continuously predicting the probability of the next token based on the prompt and the previously generated content. However, when it comes to areas they are unfamiliar with, they don't realize their own lack of knowledge. They still chatter away, trying hard to guess what should come next. Coupled with their inability to reflect during the generation process, we often see them confidently spouting nonsense. To train the AI to give the desired answers, the first method is shot prompting. Often, we simply toss a question or instruction at the AI. This is called zero-shot prompting, meaning no examples are provided. The results may not align with what we want. But if, before asking the AI to answer, we give it a few dialogues as examples to guide it, the AI model will utilize its in-context learning ability. On one hand, it memorizes that content as knowledge. On the other, it mimics the examples to craft its response. After applying few-shot prompting, when asking the AI similar questions again, it can provide answers that resemble the example prompts. Another benefit of few-shot prompting is that since the style of the AI's responses is likely to follow the examples we provide, we don't need to spend extra effort giving detailed instructions to the AI. It can learn and infer from the example answers provided earlier. However, few-shot prompting sometimes isn't very helpful. For example, AI is notoriously bad at math-related problems. Even if we use examples to demonstrate correct results, it often messes up when attempting them. In this example, the sum of all odd numbers is 41, not 37. The problem is that the AI takes roughly the same amount of time to generate each token. It doesn't spend more time on a token just because it requires more thought, so the calculation is muddled through, and even having correct example answers beforehand doesn't help much. In such cases, we can employ the chain of thought approach. Chain of thought was first proposed by Google in a 2022 paper, where the authors found it could significantly enhance large language models' ability for complex reasoning, especially in tasks like arithmetic, common sense, and symbolic reasoning. The method of using chain of thought is to include not only the correct result, but also the intermediate reasoning steps in the few-shot prompts we give the AI. Then, when generating a response, the AI will also mimic by producing intermediate steps, breaking down the process. The advantage of this is that smaller steps make it easier to avoid mistakes. It is like being called on by a teacher to answer a question standing up, and instantly giving the correct answer is quite difficult. But if you talk more, verbalizing your thought process, you can buy time for more thinking on one hand. And on the other, it helps us think step by step, increasing the chance of getting the right answer. Chain of thought can also be applied to many areas beyond mathematical calculations. With chain of thought, the AI can focus its attention on the current thinking step at each stage, reducing excessive interference from the broader context. Therefore, for complex tasks, it has a higher probability of achieving accurate results. In the chain of thought paper, the authors also mentioned that even without using few-shot prompting, simply adding a phrase like "let's think step by step" after the question can increase the AI's probability of arriving at the correct answer. This is a very low-cost method. Using chain of thought requires us to come up with example demonstrations, whereas this method only needs a simple added sentence for the AI to generate intermediate steps and reason on its own. A boon for the lazy, have you learned it? These prompting techniques can help you better train AI chat assistants. If you found this helpful, please give it a like or save it. If you want to learn more ways to empower AI, addressing issues like outdated data, fabrication of facts, and inaccurate calculations, stay tuned for the next part. See you in the next video. Large language models like GPT, despite being widely read, still have persistent weaknesses in certain areas, such as fabricating facts, making inaccurate calculations, and relying on outdated data. To address these issues, we can empower AI with external tools or data. Frameworks that implement this idea include RAG retrieval, augmented generation, PAL program, aided language models, and React reasoning and acting. These terms might sound obscure and confusing, but don't worry, we'll explain them one by one. The knowledge possessed by large language models is influenced by their training data. If the training data lacks sufficient coverage in a particular field, the AI learns little about it and cannot answer related questions well. Therefore, in niche or specialized domains, the AI's performance may be unsatisfactory. Moreover, internal company data, personal private documents, and the like cannot serve as training data for publicly available large language models. We cannot expect ChatGPT to answer related questions for us. So what can we do? All-in solution is to provide external documents, allowing the model to access an external knowledge base to obtain real-time and accurate data, generating more reliable and precise answers. This architecture is called retrieval, augmented generation, or RAG for short. Specifically, external knowledge documents are first split into paragraphs because large language models have a limited capacity for text input at one time. Each paragraph is then converted into a series of vectors, which can be thought of as fixed-length sequences of numbers and stored in a vector database. When a question is asked, the query is also transformed into a vector, and the vector database is searched for paragraph vectors closest to the user's query vector. Once found, the paragraph information is combined with the original user query and passed together to the AI. This way, the AI can use the external document paragraphs as context to provide more rigorous answers based on the information within. As a result, you can ask questions about any content in the external documents, even if the AI model was never trained on that content. RAG is beneficial for building corporate or personal knowledge bases. Some ChatGPT plugins are based on the RAG architecture, and OpenAI has also introduced a feature that allows uploading PDFs and asking questions about them. If you know how to use the GPT API, you can also implement your own retrieval, augmented generation with code. If you're interested, you can watch our follow-up course on large language model application development. Another issue with large language models is that we cannot use them as calculators. When we ask them to perform a mathematical calculation, they are not actually doing the computation. They are simply guessing the next most likely token to generate a response. If we want the AI to act as an online store customer service agent, it might eloquently introduce products, but also give customers incorrect order totals, which is dangerous. But what if we don't ask it to do the calculation and instead provide it with the computed result? Program-aided language models, or PAL for short, can help us address such problems. PAL was first proposed in a paper in 2022. The core idea of PAL is that instead of having the AI directly generate calculation results, we leverage other tools better suited for computation, such as a Python interpreter. Our instruction to the AI then becomes, when calculation steps are involved, generate the code needed to obtain the result. Specifically, to ensure the AI follows our requirements, we can use chain of thought prompting. If you're not familiar with chain of thought, you can watch the previous video. First, in the prompt, we use few short examples to demonstrate step-by-step thinking to the model, showing how to write variable assignments, mathematical operations, and other code needed to solve the problem, so the model can mimic the approach. After the user asks a question, we combine the user's question with our existing prompt template and give it to the AI to generate the code. Next, we take the AI's response and feed it to a Python interpreter, which executes the code and returns the calculation result. This result can then be passed back to the AI, allowing it to properly respond to the user's question with the computed answer. In essence, we are leveraging the large language model's ears to receive questions, brain to think, mouth to speak, and the code interpreter's hands to perform calculations. ChatGPT's advanced data analysis feature can be seen as an example of PAL. With its built-in Python interpreter, ChatGPT can use programming logic and code execution to answer questions more accurately. If you know how to write code, combining the GPT API to implement program assistance is also relatively straightforward. Another limitation of large language models is that the knowledge they possess is inherently constrained by the date of their training data. For example, its training data certainly does not include this year's news, so the model cannot know about events that occurred after its training was completed. This is known as the knowledge cutoff. When we ask the model about recent facts, it may either provide outdated information or fabricate answers entirely. However, retraining the model is quite costly and does not completely solve the problem of outdated data. It would be great if the AI could search the internet for information it doesn't know and then tell us the answers. But how would it know which websites to browse or what keywords to focus on to find relevant information? A paper titled React Synergizing Reasoning and Acting in Language Models, published in 2022, proposed the React framework. This is not React, the popular front-end framework, but rather React short for reasoning and acting. The core of React is enabling the model to engage in dynamic reasoning and take actions to interact with the external environment. It can also be combined with chain of thought prompting. We use few short examples to show the model a framework that integrates reasoning and acting, meaning breaking down steps for a given problem, where each step involves reasoning, action, and observation. Reasoning involves thinking about the problem or the observation from the previous step. Action is the interaction with the external environment based on reasoning, such as using a search engine to look up keywords. Observation is reviewing the results obtained from the action. For example, if you ask a large language model with a knowledge cutoff of January 2022, which team won the Champions League in 2022, it would not be able to answer. But if we give the AI access to a search engine as an interactive tool and apply the React framework, the process of obtaining the answer might look like this. First, regarding the question, it would reason that to answer this, it needs to look up match results. Since this AI can use Bing, its subsequent action would be to search for the keywords 2022 UEFA Champions League champion. Next, it observes the results of the action, obtaining a series of web pages containing Champions League information. Based on the results from the previous step, it begins a new round of reasoning. A news website link mentions the final, so it likely contains the needed information. The corresponding action for this step is to click on that link. After entering the web page, it observes a passage mentioning the winning team, along with details about the final opponent and score. It then continues reasoning based on this information. The next step should be to cite the information and provide the answer to the user. Therefore, the final action is to summarize the found information and present the final answer to the user. Through React, we can see the model's step-by-step problem, solving trajectory toward the answer, which is quite similar to how humans approach tasks. By using step-by-step reasoning via chain of thought, the model can not only obtain more accurate answers, but also allow us to verify the process through these trajectories. Furthermore, the observation and action steps increase interaction with the external environment, helping the model overcome certain inherent limitations. For example, inputting keywords into a search engine or viewing information on web pages can mitigate the impact of knowledge cutoff. Features like ChatGPT's web browsing function enhance its ability to interact with Bing search, enabling it to answer questions about real-time information. This helps users verify the reliability and authenticity of information sources. Additionally, the action in the React framework is not limited to searching and browsing the web. It refers to any action the AI model supports. For instance, if the model can interact with a code interpreter, running code can be an action option. If it can access external documents, searching for keywords within those documents can be an action option. If it can call an application's API, interacting with that application can also be an action option to leverage different external data and tools for the model programmatically. Frameworks like LaunchIn can be used to simplify the process of building large language model applications. If you are interested, you can watch our introductory course on large language model development. I hope this series of educational videos has helped you build a better understanding of generative AI, large language models, and the technical foundations behind popular applications like ChatGPT. While others may feel overwhelmed by the constant emergence of dazzling new applications, you can remain steady and adaptable. If you found this helpful, don't forget to give it a like before you go. See you next time.